What's up, everybody? Well, same as last time. Right now, there's nobody. But soon there will be everybody. All right. Oh yeah. If you are watching this not live, then I will be starting in 5 minutes. I will also put a timestamp in the description. Starting at 4:05. Okay. Sad. Our one viewer left. Oh, and I need my phone. We have a viewer. Let's go. Can we hit 2 viewers, guys? Can we hit 2 viewers? If we can hit 2 viewers, you know, if we only have 1 viewer, that's fine. That's fine. If we could hit 2 viewers, though, I would do a 2 viewer giveaway of knowledge. Okay. Pigeonhole Principle. Gotta stretch. Gotta stretch before this knowledge. I hope you guys like the thumbnail. It's still so bad because it's just badly edited, you know. I couldn't like crop it right. Like I wanted to crop it so that the top of the head was not cut off, but like I don't know, I just couldn't crop it right, or I don't even know. All right. And I was too lazy to fix it, but I think it's still, you know, it gives off the right vibe. Okay. It is 4:05. That means it is Pigeonhole Principle time. So, first off, structure of the stream. This will be similar to the first stream, although the math induction stream, although I have actually reviewed the solutions and hopefully, I won't spend 50 minutes on a problem that did not take 50 minutes to explain. But I'll be focusing on doing more problems and less big ideas, okay? Just to kind of show some of the clever ideas that you can come up with Pigeonhole Principle type problems. Okay, now to get the most out of these streams, the best case is that you seriously tried and you thought about many of these problems. Now, I understand, I totally understand if you're more just looking to see some interesting solutions and ideas. But I will say that they will be more compelling if you've tried the problems. I would say at least read the problems beforehand in the document, because otherwise you may have difficulty understanding the premises of them. Especially this week, a lot of the problems, the premises are kind of they're a bit hard to digest right away and take some time breaking down. So if you're already lost on what the actual premise of the problem is, then you really don't have much of a chance of kind of understanding the solution, right? Okay. But of course, I'm not trying to assign you homework or something like that. Okay. If you just want to watch these, just to watch them and just to kind of consume the information, that's also really great. Okay. Now the pigeonhole principle. The pigeonhole principle is a very interesting idea. Okay. For many, at least in my opinion, for many reasons. Okay. The pigeonhole principle basically states that if you have n+1 pigeons and n holes, and every pigeon has to go in a hole, then 2 pigeons have to go in the same hole. Okay. Let me use an example. So let's say n was 4. So you had 5 pigeons and 4 holes. Okay. So here's our holes: hole 1, hole 2, hole 3, hole 4. Okay, that was really badly drawn. That's okay. And you got 5 pigeons. Okay, I'm gonna use the classic math teacher. I'm not an artist. Okay, so I'm just gonna write P1 and P2, P3, P4, P5. Okay, now each of these goes in a hole. All right. So you can think okay, if I put each in a hole, right? Let's say I put 1, 2, 3, and 4 in the 4 different holes, then P5, has to go somewhere with everyone else, right? And it doesn't matter how you divvy these up. 2 pigeons have to go in the same hole. Now on its face, when you just think about it, just a couple seconds, okay, this is intuitively quite obvious. Okay, I feel like you don't really need a mathematical background to be able to conceptualize if I have 10 objects and 9 boxes, and I want to put an object in each box, then some box is going to have 2 objects, right? But what's really interesting, in my opinion, about the pigeonhole principle is that it's incredibly powerful when you apply it in non-trivial ways and non-trivial scenarios. So in this way, it's much like the triangle inequality. The triangle inequality on its face is also, in my opinion, intuitively obvious. Now, that's not meant to be if you have difficulty understanding it, that's not meant to talk down on you or anything. That's just compared to some other mathematical results, it's a little bit easier to digest. But anyway, the triangle inequality, it's obvious on its face, but it's extremely useful, and it's also deceptively difficult to correctly apply, right? And the same is true of the pigeonhole principle. It's deceptively simple, okay? Because it's really not, like I said, it can be applied in a lot of non-simple ways. All right, so now the more general statement of the pigeonhole principle says that if you have kn+1 objects, I hope that's not blurred out by the glare. You have kn+1 objects, and you have, I think, n boxes. Then some box has, what do you think the answer is? Like Dora style, what do you think it is? The answer is some box has k plus 1 objects. Now, this is a little bit, you got to think about it a little bit more, but I think it's also not too bad to try and digest. So like, let's say, you had, let's say k was 4 and n was 5. So you have 21 objects, k was 4, n was 5, and you have 5 boxes. Okay, 21 objects, 5 boxes. Then some box is going to have at least 5 objects. And the reason is, if you think about trying to make every box have just 4, then you can only divvy up 20 of the objects, right? So there's always like one left over there's always one left over, and some box is going to have, that one left over. Okay. Now, if you were to actually, now this is more kind of like an observation, although if you actually wanted to prove this, what you could do is you could say like, let A sub j, okay, it's not that important, but you could say, let A sub j be the number of objects in box J. Okay, A sub j is the number of objects in box J. J ranges from 1 to n. And then you assume that A sub j is less than or equal to k for all j. And then that tells you, well, you know that A1 plus A2 up to plus AN, that has to equal Kn plus 1. But if each of the AJs is less than or equal to k, then the maximum value of that sum would be just Kn, not Kn plus 1. So you can derive a contradiction, using proof by contradiction and this assumption. And then the natural conclusion is that some AJ must have more than k objects, or at least k plus 1 objects. All right. Enough of that. Let's get into the examples. Okay. So I included some of the examples from the section. So all of these sections in the actual book, they have examples and then they have problems. Previously, I was kind of just doing the problems, but I liked the examples that they gave here, and I also spent a lot of time with especially the last two. So I think that they're useful to go over. Now, example 1 is a pretty classic Pigeonhole Principle problem. Okay, this is a must-know Pigeonhole Principle problem. If you ever get mugged or something, and they ask you like this is, and they're going to ask you a Pigeonhole Principle problem, they might probably gonna ask this one. Okay. All right. Well, I mean, maybe something similar. Okay. Prove that every set of 10 two-digit integer numbers has 2 disjoint subsets with the same number of elements, or same sum of elements. Okay. So we have some set of 10 two-digit numbers. Okay. Let's say it's like 13, 24, 17, 85. Okay. Whatever. There's 10 of them. Okay. And we're going to look over, what it's saying is that over all the possible subsets that you could have of these, there has to be 2 subsets that have the same sum. Okay. Now, if you try to think about like proving this directly without thinking about the Pigeonhole Principle, this is actually like there's really no way you can get around using it, right? Like these numbers, they could be anything, right? Like, and to prove that 2 subsets of the same sum, like they could have different numbers of elements, right? Like the only way that I could think about somehow not using Pigeonhole Principle is doing like a ton of casework, which would be stupid and long-winded, and I don't even know if that would work. Okay. But luckily, we have the Pigeonhole Principle to help us out. Now here, if you look at the text of the problem, let me pull it back up again. You can kind of identify what your pigeons should be and what your holes should be. Okay, so what you're trying to show that over all subsets, 2 of them have the same sum. Okay, over all subsets, 2 of them have the same sum. This is very similar language to saying overall pigeons, 2 of them are in the same hole, right? So like intuitively, the pigeons are going to be like the subsets, okay? And the holes are the subset sums. And we're trying to show that two pigeons are in the same hole. Two subsets have the same subset sum. Okay, now let's go ahead and compute the number of subsets and the number of subset sums. The number of subsets, well, we have 10 elements, okay, 2 to the 10, 1024, but we're not really including the empty set, okay? I guess we can, doesn't really matter. I don't know if it says non-empty, but like obviously the empty set can't have the same sum as a non-empty set, right? So we'll say 2 to the 10 minus 1, which is 1023. 1023 subsets. Now the number of possible sums. The way we do this is we think about what is the lowest possible and what is the highest possible. And then we think about, it could be anything in between. Now the lowest possible sum is just 10, right? Just a one element subset with the element 10 in it. Okay, so it could be anything from 10 to the highest would be if you had used the entire set, all 10 elements, and they were all like 90, 91, 92, 93, up to 99. Okay, that evaluates out to, kind of winging this, so I hope I don't mess it up, 945. I believe 945. Right, because 90 times 10, and then plus 1 plus 2 up to 9 to 945. Okay, so 10 to 945, the number of numbers in between here is going to be 945 minus 10 plus 1, which is 936. Okay. And boom. 1023 possible subsets, but only 936 sums that those subsets could take on. So two subsets have to have the same sum. There's just not enough sums to go around, okay? And that's how we prove that problem. So like I said, pretty classic Pigeonhole Principle problem. Not too difficult, although, if you've never seen it before, Pigeonhole Principle problems tend to be, in my opinion, kind of difficult to kind of figure out. But this one is not too bad, I think. Oh no, I have no viewers anymore. Sad. Okay. All right. Oh, we have a viewer back. Cool. So example 2. I think I did that math right. Yes, I did. Just, doing math live is generally a bad idea. All right, example 2 is a step up, okay? Big step up from this problem. Example 2 is hard, okay? But that means it's a great learning opportunity for all of us, right? So we shouldn't shy away from that. Now, actually, this problem is an IMO problem from 1985, okay? Proposed by Mongolia. It was problem 4 in the 1985 IMO. Given a set M, okay, well, first thing, we're going to read it and we're going to break it down to understand what it's saying, because admittedly, it's very hard to actually figure out what it's saying. Given a set M of 1985 distinct positive integers, none of which has a prime divisor greater than 26, prove that M contains at least one subset of 4 distinct elements whose product is the 4th power of an integer. Okay, so we have this set M. First, that's what we're working with. We have the set M, okay? And it's a bunch of integers, a bunch of positive integers. And there's 1985 of them, okay? So 1985 positive integers, big set. And I believe they're distinct. Oh no, or yes, they are distinct. And they're distinct. Is that readable? I don't know. You heard me say it, so you should remember. None of which has a prime divisor greater than 26. Okay. Now, that's kind of a weird way to say that, the only possible prime divisors are everything up to 23, okay? So, every number in here only has, its prime factorization only has one of 8 possible primes, or 9 possible primes. Those are, so if I have some element M in here, okay, then its prime factorization is going to have only 2s, 3s, 5s, 7s, 11s, 13s, 17s, 19s, and 23s. Now, of course, it doesn't have to have all of these, or, like some of these powers could be 0, but it can't have like a 37 at the end or anything like that. And we want to prove that this big set that's defined in this weird way contains at least one subset. So we're looking at subsets of 4 distinct elements, subsets of size 4, and the product of all 4 of those, okay, we multiply them together, it's a 4th power. Okay, now let's try and let me explain my solution and my approach. Now, my solution, the way I went at this was mostly correct, but I kind of missed an important realization which would have helped me out, right? I made some good initial insights, so I'll explain kind of how I tackled this problem right out the gate. So, first thing is that I immediately considered prime factorizations, okay? Thinking about these numbers and prime factorizations. Now, like, the reason in the moment was just experience, okay? It just seemed like the natural thing to do, just from my own experience. But the actual answer of, how could you actually think to consider these numbers in prime factored form? Well, there's a few reasons. So you have this condition, right, on the prime factors of on the prime numbers that can divide into a number. So like that already kind of hints at talking about prime numbers. Secondly, if a number is a 4th power one way you can describe all numbers which are 4th powers is that their prime factorizations, all the powers of their primes are multiples of 4. Okay, so like 16 is a 4th power. It's 2 to the 4th. Okay, so like 16 we write as 2 to the 4th. Its prime factorization has a power that's divisible by 4. I mean, and so is 2 to the 8, right, which is 256. And so is 2 to the 8 times 3 to the 4, which I'm not going to try to do that live, okay? But you can figure it out yourself, okay? 2 to the 8 times 3 to the 4 is also 4th power. Each of these prime powers is divisible by 4. And one way you can see that really quickly is that, if like what you can do is just write it like you can pull out that exponent of 4, right? Because they're all divisible, so you can pull that out. And then you get this number in between, which tells you that it's power of 4. This would be 12 to the 4th, which is, again, not trying to do that, somewhere in the 20,000-ish range. Okay. So now this also applies in general. So if you want to know if a number is a perfect square, then if you look at its prime factorization, then all the powers must be even. Okay, and if it's a perfect cube, all the powers have to be multiples of 3. So I already knew this, right? And I already knew okay, it has this constraint on the prime factors, and I already know how to describe 4th powers using prime factors. So I was like, this seems like a good way to utilize the information in the problem that's given. Okay, so what I did was I said every number m is representable as this prime factorization, and all these powers I could say are, let's say this is E1, E2, E3, E4, E5, E6, E7, E8, E9. Okay, all these powers are those, and of course any of the e's, they could be 0, right? So we don't need to use all the prime factors. And what that means is really what we can do for every sort of positive integer m, we can describe it as a 9-tuple of integers, E1 to E9. Okay. So every m we can describe as, there's like a sort of 1-to-1 correspondence. Like this is a perfectly good description. I don't know exactly what the formal definition would be, but this is like very, very much well defined. So if you gave me a set of 9 integers, like 1, 2, 0, 1, 5, then I could construct a number m which could possibly be in this set. Okay, so we have 1985 9 tuples of integers. And we want to show that some product of 4 of them is a multiple of 4. So what that means is, okay, so when we multiply two numbers, we, like their prime factorizations, when we multiply two prime factorizations, we add all the powers, right? So what that is basically saying is that there has to be some 4 elements such that if you look at these 9 tuples at least, okay? So you have some, you have some 4 of these like 9 tuples, and when you add them together, you add all those powers in each column, then you get a 9 tuple which has like powers that are all divisible by 4. Okay, that's probably a bit of, I might not have explained that super clearly, but that is the idea. Now, another important realization to make about these powers is that we only care about their values mod 4. Okay, so what that means is, like, if you have some 4 numbers, let's say A, B, C, D, and it equals a power of 4, right? And let's say A and its prime factorization has a power of 2 to the 5th, right? Then we don't care that it's 2 to the 5th. Really, all we care about is that it's 1 mod 4. And the reason is because we could divide here both sides by 2 to the 4th, right? And we'd still get a perfect 4th power, right? If you divide like a 4th power by another 4th power, and like the result is an integer, then it will still be a 4th power because we're just slicing off powers of 4 from the prime factorization. So not only do we only need to look at these 9 tuples, but we only care, like these 9 tuples, we only care about their values, like mod, each of the individual values mod 4. Okay. So once again, every number m, of which there are 1985, we're associating a 9 tuple, and each of the values in that 9 tuple is going to be 0, 1, 2, or 3. And we want to show that of these 1985, if we pick 4 of them, then some 4 of them have to, when we add them all up, you get a multiple of 4, like for each element, and the resultant 9 tuple. Now, I will save you the time because I did it myself. This is very hard, and I was not able to figure out how to show this. Okay. And this is where I kind of got stuck. Now I'm going to explain the actual solution, which uses a lot of the same ideas, but it makes a very clever realization, which is that if we want to show that a product of that something is a 4th power, it's sufficient to show that it's the square of a square. Okay, the square of a square. And the reason that's useful, well, okay, here's one way that you could think about this, right? Because that seems like, I mean, here's one way you could think about this in the problem. When you start trying to add up these 9 tuples, right, of numbers from 0 to 4 or 0 to 3, there's a lot of them, right? In fact, there's 4 to the 9th of them, which is not totally sure. I think 252. No, I shouldn't be doing this. It's something like that. I shouldn't be doing this, but it's big, okay, and it's way bigger than 1985. That's for sure. So you really can't apply the Pigeonhole Principle. You can't say like, oh, there's some 2 which are the same, right? Which is like a classic application of the Pigeonhole Principle. But if you considering 4th powers is difficult, so a common strategy is to consider a problem that's easier. And an easier problem is if you only considered squares, right? So like if these were only 0s and 1s here, right? i.e. we're just looking at the parity of all of the powers. Then there's only 2 to the 9, which are 512 possible like 9 tuples here. And that means that there's going to be a lot of 9 tuples which are the same, right? So the way you could think about the squares, about considering like squares of numbers, is by considering an easier problem, which is a very common problem-solving technique. Okay, So what we'll do is we'll take all of our 1985 numbers and we'll consider just the parity of the powers and the prime factors. So we get 9 tuples, which are just have value zeros and ones. And there's only 512 of these total, right? We have 1985 of them. So now the next question is how many will overlap, right? How many do we know for a fact must be the same, right? How many pairs can we get? Because every pair of 2 of them, every pair, when we add them together, then that will be a multiple of 2, right? Every element will be a multiple of 2 because they're the same. And if we can somehow take all of those pairs and add them together, then we get a bunch of numbers which are multiples of 4, right? And that's going to be how we're going to solve it. So now, after kind of playing around with this, what you should notice, again, if you just mess around with this a little bit, what you realize is that, if we wanted to avoid pairing as much as possible, then what we would do is the first 512, we make them all distinct. And then, actually, I'm trying to think of how I want to explain this. Okay, well, the gist of it is this. If you have at least 3 times 2 to the n plus 1, in this case, n is 9. If you have at least this many objects, right, or this many 9 tuples, then you will have at least 2 to the n pairs, or 2 to the n plus 1 pairs, which are the same. Admittedly, I should have reviewed this more beforehand, why this is the case. I kind of just got it from experimentation, and but that's not always like super reliable. One way I guess you could think about this is, well, I'm not actually totally sure. I'm going to be honest. I actually am not totally sure how you would demonstrate this. I'll have to think about it more. But yeah, I'm actually not totally sure. So I know that that's very unsatisfying, but I'm gonna have to skip over this and move on. Like I said, if you just experiment with this, you will be able to show that this is, to kind of intuitively reason why this is the case. Okay, so what that means is, and we have 1985. Okay, so 3 times 2 to the 9 plus 1 would be 1537. So like we have at least 3 times 2 to the n plus 1 objects. And what that means is that at the end, we'll have at least 2 to the n plus 1 pairs, right? Which are the same, okay? Which in this case would be 513. Now, so what that means is that we have at least 513 pairs, right? So that means that, like, if we imagine taking all of those pairs, so every pair is going to look like, this. It's going to be, so if we add 2, which are the same, right? If we add 2 9 tuples, which are the same, then what we get is 0. We get a bunch of 0s and 2s, right? Get a bunch of 0s and 2s. And you can imagine, okay, how many 9 tuples are there which have only 0s and 2s? It's still 512, right? It's actually kind of, it's almost the exact same, like combinatorics wise, as this initial setup, right? So what that means is that, like, we have at least 513 of these 9 tuples, which are 0s and 2s, and that means that at least 2 of them must also be the same. So there must be at least 2 9 tuples of 0s and 2s, which are the same. And when we add those together, we get a 9-tuple. Oh, this is really messy. We get a 9-tuple, which has zeros and fours, which is like all of its prime powers are divisible by 4. Okay. I apologize. I think I should have reviewed that a little bit more. I already knew I was going to have a bit of a tough time explaining that one. But I think at least some of the important ideas, which I kind of was able to touch upon. One of the really important ideas is being able to figure out how to utilize the information of a problem, or at least describe the objects in a problem in a way that is uniform and useful. Okay, so when they tell us the setup that m is 1985 distinct positive integers, I mean that could be anything, right? I mean any 1980, those integers, they could be anything. And there's really the only common thread they give you is that the prime divisors are less than 26, right? And so it's really important that you utilize that common thread between those to be able to describe each integer in a sort of unique way that utilizes sort of the properties that right? And that's kind of what I was explaining with describing every number as a 9-tuple of numbers from 0 to as basically a 9-tuple, which each element represents the power of a prime. Okay. All right. Let's go to the next one. I feel a little unsatisfied about that one because I wasn't really able to demonstrate the one of the important ideas, but I think that we should just move on. Okay. What's the next one? Oh, example 3. Okay, so example 3. This is actually a Putnam problem, B2 from 2006. This one is also, I actually did not get this one. This one's also a bit difficult, okay? But I think I'll have an easier time explaining it. Okay, so let's first break this problem down. Now, the way it's written is super formal. It looks super convoluted on its face. It's really, I think I can explain the idea, pretty conceptually. So, prove that for every set x equals x1, x2, up to xn of n real numbers, there exists a non-empty subset S of x and an integer m such that it gives you an inequality. Okay, let's break it down. So, we have some set x of n real numbers. All right, and these could be anything, any real numbers, okay? And we want to show that there's some subset, right? Some subset of these real numbers and an integer m such that the absolute value of this integer m plus the sum of all of the elements in the subset, okay, so the subset sum, is less than or equal to 1 over n plus 1. Now, all this is saying is that there must be some subset of these real numbers such that when you add all those elements together, it gets within 1 over n plus 1 of an integer. Okay, it gets sufficiently close to an integer value. So for example, if n were equal to 10, then what this is saying is that if you have any set of 10 real numbers, then you should be able to find a subset of those real numbers such that when you add all those together, you're within 1/11th of an integer. So you're either 1/11th more than an integer or 1/11th less than an integer, and you're in that range. Okay. So, and the sort of idea of why this is true, right? A vague intuitive idea of why this is true is that as you have more numbers to work with, you should be able to have increasing precision, because increasing precision to an integer, because you have more subsets and more opportunity to hit your target. So if you had 1,000 numbers, right? If you had 1,000 numbers, there are so many possible subsets, 2 to the 1,000, minus 1 if you don't include the empty set, all these possible subsets, then it's the same as saying that you should be able to find some subset which gets within 1/1000 and 1/1001th of an integer, which is very close, very precise, but you have a lot of room to work with, right? Okay, so an important note. We only, in this problem, and this is going to help simplify things without loss of generality, right? We only really care about the fractional parts of these numbers, okay? So all we care about is that we're getting within a certain range of an integer, right? So if one of these numbers, let's say x3 plus x4 plus x7 is close to 7. Okay, let's say it's within 1/10 of 7. Okay, so it's like between 7 minus 1/10 and 7 plus 1/10. Oh, we had a second viewer there for like a couple seconds. Kind of sad. So it's within this range. Then let's say x3 was like 5.13 or something like that, right? Then we could subtract 5 from x3, make it just 0.13, and we'd still be within 1/10 of an integer. That integer would just change to be 2. So the point is, like, if the sum gets within a certain range of an integer, if we subtract integer values off of like the elements, then it's still going to be that close to an integer, just a lower one, right? So we only care about fractional parts here. What that means is, like, and that's actually really, if you think about how much that simplifies our problem, it simplifies it a lot, because we're looking at sets of real numbers. It could be any real numbers, right? And instead, we're only looking at real numbers between 0 and 1. Okay. Now, I guess actually, if you want to be nitpicky, right, the cardinality of both those infinite sets is technically the same, but it helps our brains a little bit more. Okay, our finite human brains. Okay, now let's conceptualize the problem. Let's conceptualize what's going on. And also, we only care about the fractional parts of the sums as well. Okay, so if the subset sum is between 7 minus 1/10 and 1/10, 7 plus 1/10, we don't really care that there's the 7 there, right? We could subtract those integer parts as well. So what we can imagine doing is looking at the interval 0 to 1. Okay. And every subset, we're plotting every subset sum, okay, the fractional part of every subset sum. Now, there's 2 to the n minus 1 subsets, right? 2 to the n minus 1 subset sums distributed across this line. And what it's saying is that at least one of them is going to be in this magic range, okay? I don't know why I described it as a magic range, just this special range, okay? Either its fractional part is between 0 and 1 over n plus 1, or it's between 1 minus 1 over n plus 1 and 1, right? Because it could also be close to an integer on the left side of it. Now, when you really try to think about this, right, we have a vague intuitive idea of why it's true, but a really good question you can ask yourself when you're not sure exactly why something is true is just like, basically just what gives, okay? What gives? So why is it the case that this always has to be true? Why can't all of our subset sums, we have some set, and why can't all of our subset sums just nicely be in the middle here? Right? Why can't we have that be the case? It seems like, that should be possible. Right? Why do we always have to have 1 in here? So, like, this is a good technique to, like, I don't know. I feel like this is also a common technique, like, just in the real world, Well, I mean, math is, well, like this applies broadly. Like when you don't know why something is true, you kind of ask like, why, like, well, what gives? Like, why can't it be false? You ask like the, I don't know what you call that, double negative of the question. But anyway, not important. It's important for math, okay? And that's what matters. So, all right. So, one important sort of reason, quote unquote, is that these aren't just random numbers. These aren't just random sums, okay? It's not like we're just plotting 2 to the n minus 1 random sums on this interval, right? They have they're interconnected, right? Because they're all based on the same set of elements. So we can't just have those subset sums have any structure we want. Like they can't just be distributed in any way we want. They have to have some kind of pattern to them. And presumably that pattern is this, that one must always kind of lie in close to the ends. So these sums are very interconnected, and they have important relationships between them. And so, for example, one relationship between the sums, which will become very important, is a relationship between a superset and a subset. Okay, now superset and subset are relative terms. If A is a subset of B, B is a superset of A. Okay, so but I'm gonna kind of broadly talk about like a set and its subset, or a subset and its superset as a subset and its superset, so you kind of know which one I'm talking about. Okay, so let me give an example. Let's say that x3 plus x4 plus x5 plus x8 plus x9 is 6.5. Okay. Sorry, I just got a text. Okay, let's say this is 6.5. Okay, and x3 plus x4 plus x8 is 4.4. Okay, now what we have, yeah, I'm not now. What? Okay, thank you. Ridiculous. How dare he interrupt my Pigeonhole Principle stream? God, parents. Anyway, you know how they are. Okay, anyway. So what we have is a set, and we have its subset, right? Or a superset and a subset. And what's important is that if we have, like, we know the sum of a superset and the sum of a subset, then we can construct another subset which has a sum which is the difference of these two, right? If we just don't include those elements, right? So what that means is, like, what we can do is, instead of showing that some subset sum is within 1 over n plus 1 of an integer, what we can do instead is show that some superset and some subset have sums which are within 1 over n plus 1 of each other. Because then when we subtract, or within 1 over n plus 1, their fractional parts are within 1 over n plus 1 of each other, right? Or they're within 1 over n plus 1 of each other, plus or minus an integer, right? So we want to show that two subset sums, they're sufficiently close together, right? So that when we subtract them, we can construct another subset which is really close to an integer, right? Now, specifically, we want to show that the superset and the subset, they're within 1 over n plus 1 of each other, right? Because that's like the precision threshold we need to prove this problem. Now, the next realization. Okay, well, let me try to explain how you could think of the solution. So there is a really clever realization you can make, and I have a difficult time thinking about how I would think of it, but I will try my best to explain how you could. Okay. So we have all these numbers. Okay. Fractional parts are all from 0 to 1 of these subset sums. We want to show that sum 2 between a superset and a subset, some 2 are within 1 over n plus 1 of each other. Okay? So we can imagine, here we got 1 over n plus 1. We could split this up, 2 over n plus 1, right? So we split this up to 2. This here is n over n plus 1, right, into n plus 1 intervals. And we want to show that a subset and a superset must both lie in the same interval. Okay? That's enough. Now, the problem is, if you just had you pick some arbitrary subset, some arbitrary superset, then you could just you could spread them apart, right? But if you had somehow a chain of subsets and supersets, right? We have some set, and then you have a superset, and then a superset, and then a superset, and then a superset, right? If you had enough of those, then when you put them on this line, some 2 have to lie in the same interval. In the same way that if you have enough pigeons, some 2 have to lie in the same hole, right? And specifically, what we need, well, okay, first off, if one of those sets lied in our special range, then we'd be done. Okay, so we're just not going to really consider placing them in these intervals. So we're really only considering n minus 1 intervals here. Okay, so if we had some chain of n subsets and supersets, then we know that some 2 of those n, some 2, must lie in one of the n minus 1 intervals. And so you think about, okay, how could I think of a chain of subset to superset to superset to superset to superset that's n long? And the answer is x. You have x1, and then x1 plus x2, x1 plus x2 plus x3, x1 plus x2 plus x3 plus x4, up until x1 to xn. So what we have here is that any 2 of these, now I wrote these as sums, not as sets, but same idea. Any 2 of these sets or sums, right, they have a superset subset relationship. Okay. Now, that may have been a really convoluted way of explaining how you could think of, the answer to how you could think of this might just be oh, I just guessed it, right? Just guess and check. Because sometimes, you think of an idea to a problem and it's just correct, and just because you kind of guessed that it was correct. And you know what, that might be the answer. But I always like to think that there's a deeper reason that you can always figure something out, right? At least whether or not that's true, I don't know, but it's certainly a productive mindset to have. Okay, so what we have here is n. We have n of these, right? So we have n of these. If we plot other subset sums, then some 2 must lie in the same interval because we have n minus 1 intervals. And if they lie in the same interval, their difference must be, so their difference is, at least the fractional part of their difference is less than 1 over n plus 1, or less than or greater than 1 minus 1 over n plus 1. And we've proven the problem. Okay. So the way you'd write this proof is you consider these sums. Then you say if one of them lies in here or in here, the very ends, then we're done. So then we consider the case where none of them lie in those ends. Then we can show that some 2 lie sufficiently close to each other. Take their difference, and we have constructed a subset sum which is within 1 over n plus 1 of an integer. Okay. All right. I'm pretty sure I probably I may have explained the same thing 5 times there, but I apologize if I did that, because these problems are still kind of fresh in my mind. I was working on these problems just a few days ago, a couple weeks ago, and some of them I still don't fully get myself, so I'm also kind of trying to work through them as well. Okay, now done with the examples. Now we're going to take a little bit of a breather, and we're going to do a pretty straightforward PHP problem. PHP. Is that a drug? I hope not. Okay, that would not be good. Now, problem 33. you have given 50 distinct positive integers strictly less than 99. Show that some two of them sum to 99. Okay, so what we do here is, now, like I said, this is a standard problem, so I'm going to give you the unsatisfying answer of, oh, this is just how you do this problem. Okay, I'm not going to try to really intuit the solution too hard. But these numbers, they could be anything from 1 to 98. Okay, and we want to show that no matter what subset of 50 we make, some two elements must sum to 99. So like, let's say, oh, it so happens that 47 and 52 are in our set and they sum to 99 or something like that. Okay, so what we can do is we can pair up the term. We can take each of these 1 to 98 terms and we can make pairs where each of the pair, like if we add each number in the pair together, then they equal 99. So we can imagine splitting up our possibilities like this: 1, 98, 2, 97, 3, 96, up until 49, 50. And this is where we apply the Pigeonhole principle, because there are only 49 pairs here, and we have to pick 50 numbers, right? So we have to pick 2 numbers from the same pair. If we try to pick only 1 number from each pair, then we can only pick 49 total, and then we have to pick 1 more, right? So that means is that we need to pick 2 numbers from the same pair, and those 2 numbers that we pick from the same pair, let's say it's those 2, those will sum to 99. And that is the problem, okay? Pretty quick problem. Okay, let's go to the next one. And once again, a little bit more of a challenging problem. All right, but you know, those are the ones you learn the most from. Okay, problem 34. Problem 34 says, a sequence of m positive integers contains exactly n distinct terms. Prove that if 2 to the n is less than or equal to m, then there exists a block of consecutive terms whose product is a perfect square. Okay. Now, I did actually solve this problem, which is great. And one of the things that really helped me was just by kind of messing around with it a little bit. And picking values for n and m to kind of test cases, right? This is a very common strategy. So let's say n was 3, okay? So I would have like 3 distinct terms. And I had 3 distinct terms, and I have to make a sequence that's at least 8 long. So our sequence is at least 8 long. Okay. So now I just said, okay, let me just throw some random stuff down, okay? Make some sequence 5, 6, 5, 7, 6, 5. Holy, 5, 6, 5, 7. Watch me fail doing basic addition live. 6, 5, 7, 5, 6. Okay. All right. So this is 9 elements long. Okay. Now really we can make it 8, but I was like, let's spice it up. Let's make it 1 more. So what we want to do now, what the problem statement says is that there must be some block of consecutive terms here where the product of those consecutive terms is a perfect square. So let's try to find it, okay? Now, if you mess around with this a little bit, you will notice that this block can be found here. the first 8 terms. Okay, why is that the case? Well, we have 1, 2, 3, 4 5s. Okay, 1, 2 6s, and 2 7s. Right, and when you mess around with this, what you realize is that in order for something to be a perfect square, then you want to have an even number of each of the distinct terms. Right. Okay. Now let me grab my notes for. Yeah. So you want to find a consecutive sequence which contains an even number of each distinct value. Okay. Now what we're going to do here is apply some ideas we've seen previously. Okay. So from example 3, the one we did with the subset sums, what we did was we represented every sort of. Okay. What we did was any kind of consecutive like sum that we had, like let's say x3 plus x4 plus x5. Okay, we represented as the sum, as the difference of 2 prefix sums. Okay, so we only considered like sets and sums that started at x1, right? So a prefix sum or a prefix sequence is a sum or sequence that starts at the very beginning of a larger sequence. Okay, and so this idea will come in handy for this problem because what we can do is represent every consecutive block of terms, or at least the product of every like consecutive block of terms, as the product of a prefix sequence, and then divided by all the terms that we left out, like at the front, right? Another prefix sequence. And there's only m total prefix sequences, right? So there's a lot of different sort of consecutive blocks we could think of, but now we only have to think about m prefix blocks. Granted, we're looking at the difference between 2 of them, which will complicate things a little bit, but this idea will come in handy. The second idea is from problem 2, or example 2. Now, notice that we only care about the parity of the number of appearances of distinct values. So in our example, the sequence had 4 5s, 2 6s, and 2 7s. But honestly, it doesn't matter. Like it could have 20 5s and 6 6s and 14 7s. It doesn't actually sort of matter what that number of the appearances is. What matters is that it's even, right? What matters is its parity. So we need some way of keeping track of the parity of the number of appearances of a value. Okay, and again, we're considering prefix sequences. Okay, of which there are m. So what we want to do somehow is define, somehow be able to keep track of the number of appearances of distinct values from beginning to any position, say j in the sequence. And right, we only care about prefix sequences, and the there's this 2 to the n in the problem, right? There's this 2 to the n. We need to have at least 2 to the n terms in this sequence, which seems like 2 to the n that can't be arbitrary, right? Like it seems like very specifically chosen. And all of these things culminate, hopefully, to suggest the following solution I will present that I thought of. Okay, like I said, I really can't give a specific motivator for the solution other than like a lot of different sort of factors at play, and I may have just gotten kind of a little bit lucky in like being able to think about this. So what I did was I defined a binary number, or I guess you could, yeah, I defined a binary number b sub j as, so it has n digits, okay? So n digits, 1, 2 to n. And what this b sub j is it's gonna refer to the prefix sequence, which starts at position 1 and ends at index j. Okay, so we have m b's. Okay, so we could have anything from b1 to bm. Now each position here, so digit I will correspond to the parity of the number of appearances of value I. Okay, so what we do is, like in the previous example, we had 5, 6, 7 were our numbers. So we could say we can number like 5, we can number 1, 6, we can number 2, and 7, we can number 3. Right? It doesn't matter as long as we can order them somehow. And what we'll do is, if like let's say 5 has appeared an even number of times from the start, then we'll put a 0. And if it's appeared an odd number of times from the start, then we'll put a 1. Okay, so we get some kind of, for every value j from 1 to m, we can define this binary number, and this is it's like a log basically of, it says, oh, there's an even number of value 1, an odd number of value 2, an even number of value 3, and there's an odd value number n, right? Helps us keep track. Now you can also think of this as like in the example 2, we used n tuples, right? So we use n tuples of zeros and ones. I thought of it like a binary number, just because I don't know, really no reason. If thinking about this as an n tuple is more intuitive for you, then think about it in that way. Okay, so we have at least 2 to the n of these, right? We have at least 2 to the n binary numbers, which are n digits long. And what you should realize is that the number of possible binary numbers that we could have that are n digits long is 2 to the n, right? So we could have all zeros, 0 up to 1, 0, and then 1, 0, right? Or that's a bad way to explain it. Really, the best way to explain it is that for each digit, we have 2 options. So there's 2 to the n possible binary numbers of length n. So what that means is, well, 2 things can happen. Now, it is possible that all of these binary numbers could be distinct, okay? But if they are distinct, then that means that they cover, so from 1 to m, right? Let's say m equaled 2 to the n, and all the binary numbers were distinct. Then there must be at least one b sub j, which is all zeros, because we have to cover all the possibilities, right? There's only 2 to the n possibilities. We have to cover all of them. And for this b sub j, which is all zeros, that means that from the beginning, from position 1 to position j, we have an even number of 5s, even number of 6s, even number of 7s. Boom, we have a consecutive sequence which has a product that's a perfect square. Otherwise, if none of them are equal to 0, then there must be some 2 which are the same, okay? So there must be a b sub j that looks like this, and there must be another b sub k, which is the same. Pigeonhole principle, right? Too many pigeons is not enough holes, okay? And what that means is, if we think about what that means, let's say j is less than k, okay? Then imagine like traversing the list from j to k. Then we don't actually disturb the parity of any of the appearances, right? So like, let's say there were 3 5s up to j, and now there's 5 5s up to k. And let's say there's 2 6s up to j, and now there's 8 6s up to k. Now, what that means is that in between j and k, we must have an even number of appearances, right? Because if we had an odd number of, let's say, 5s from j to k, then the parity of the first value would switch, right? So what this means is that and boom, bingo, we found a consecutive sequence, namely the sequence, I suppose the sequence which starts at j plus 1 and goes up to k, I believe. Yeah, the sequence from j plus 1 to k, which has an even number of each term, and thus the product of all of those terms in that consecutive block are, it is a perfect square. Okay, I like that problem. Okay, I guess part of me likes it because I thought of this. A big part of me likes it because I was actually able to think about this. Now, as a reminder, this is a difficult problem to explain. Okay, like this is a difficult problem to explain, like how you can motivate it. And if you are confused about the solution, I urge you to write it out and to like try this problem out and write out the solution for yourself. The idea, like I said, the idea kind of feels like it comes out of thin air if you've never seen this before. Like, how did I think of this, right? But I think as you work with the problem more, it sort of becomes clearer, like how you could think of this. All right, but let's move on. All right. We've got two more problems that we're going to go over. And the next one isn't too bad. Now, the next one says that you have a sequence of integers. 1 is equal to x1, which is less than x2, less than x3, less than xn plus 1, which is less than or equal to 2n. And I'm being a little sloppy. Okay. So you have a sequence of integers, and it's actually an infinite sequence. But we know that at every point, like every value of n plus 1, then it's less than or equal to 2 to the n. So we have like this upper bound that's constantly constraining the top of the sequence. And we want to show that basically if you gave me a number, any positive integer, 26, okay, let's say, then I should be able to find two terms in this sequence which have difference 26. If you said 27, I should do the same for 27 or 192 or 1024, right? I should be able, for every positive integer k, there must be integers I and j such that k equals xj minus xi, okay? Now, from an intuitive standpoint, again, you can get a vague idea of why this must be true. You know, because it's constrained at the top like this, and this is pretty stringent because these are also like, this is also a strictly increasing sequence. You sort of realize like this is a very heavily constrained sequence. A lot of the numbers are really close together. And so it sort of makes sense how for any sort of like number you gave me, I should be able to find a difference. Like if these numbers were super spread apart, then like if these numbers were really spread apart, then it seems more natural to think that you could give me a number where I couldn't make two terms the difference because everything would be spread apart. But because everything's so condensed, then you should be able to do this. Again, I'm speaking very vaguely here because it's important to get a vague intuitive idea of why something is true, but that's really not a great like, don't get too cocky that you actually understand what's going on. You know what I mean? You always have to be open-minded to understand how something behaves and works. Okay. Now what we'll do is a classic strategy. We're going to test small cases of k. And what we're going to do, oh my God, what we're going to do is see how long we can hold out, basically, right? So we're going to, so one of the ways you can try to convince yourself something is true is you try your hardest to prove it false, right? And, but it still ends up being true. So first, k equal to 1. Now, we know that x1 is equal to 1. That was defined. And x2, so xn plus 1 is less than or equal to 2n. So xn is less than or equal to 2n minus 2. And x2 is less, so then x2 is less than or equal to 2, okay, when you plug that in. But it's also bigger than x1. So x2 must be 2. All right, so x1 is 1 and x2 must be 2. You can easily see this when you just like use the condition, okay? And then, well, boom, we found our two that have difference 1, right? So for k equal to 1, it must happen in the first two terms, right? In the first two terms, k equals 1 must happen. Now k equal to 2. Once again, we have 1, 2, and now the next number. Now, x3 could be 3 or 4 using the condition, okay? It has to be less than or equal to 4, and it has to be bigger than 2. But either of those, we get screwed because if we're trying to avoid k equal to 2, right? Because if it's 3, then we have, 3 minus 1 is 2, and if it's 4, we have 4 minus 2 is 2. So no matter what we pick here, 3 or 4, right? 3 or 4, we know that k equal to 2 must happen in the first 3 terms. Okay? Now k equal to 3. 1, 2. We have some freedom, 3 or 4. Let's do casework. Let's say we picked 3. The next number, x4, is less than or equal to 6. x4 could be 4, 5, or 6. But if it was 4, 5, or 6, we could, if it was 4, that, 4 minus 1 is 3. 5, 5 minus 2, 6, 6 minus 3. So if it's, if this is a 3 here, then we can only hold out for 4. Okay? If this was a 4, then we already have that difference of 3. Okay? So we can only hold out for 3. So no matter what, for k equal to 3, so 4 or 5 or 6, for k equal to 3, that must happen in the first 4 terms. Now, you may already see a pattern emerging, right? K equal to 1 must happen in the first 2. K equal to 2 must happen in the first 3. K equal to 3 must happen in the first 4. Now, seems like the pattern is, k plus 1 or something like that. But let's not jump on that too quickly, okay? This is a very important for you to realize. Sometimes like, I'll be doing like, I'll be trying to find a pattern, and it'll be like k equal to 1. It'll be like the 1 will correspond with 1 and 2 will correspond with 4. And I immediately am like, oh, it must be the squares or something, right? Because like 1 squared is 1 and 2 squared is 4, right? But like you do not want to be extrapolating a pattern from like 2 terms, right? It's good to like have it in the back of your head, but you really don't want to jump to conclusions with patterns too quickly, and your natural tendency will want to be to jump too quickly. All right, so let's do one more, k equal to 4, to really confirm our conjecture here, or convince ourselves the conjecture is true, right? Of course, this isn't a sufficient proof, right? Like, you can't proof by exhaustion this. Okay, there's an infinite number of k's. All right, but all right, let's look at k equal to 4. Now, 1, 2. We could have 3 or 4 here, so let's casework. Let's say 3 was 3, or x3 was 3. Then the next number could be 4, 5, or 6. Now, we don't want it to be 5 because 5 minus 1 is 4, and we don't want it to be 6 because 6 minus 2 is 4. So if this is 3, then this next one must be 4 if we want to hold out farther. Now, the next number, x5, is less than or equal to 8. Could be 5, 6, 7, or 8. But 5, 6, 7, or 8, you have a difference of 4, right? 1, 2, 3, 4. And then 5, 6, 7, 8, there's always like a difference of 4 there, right? No matter what you pick for the x5. So if this here is 3, then we can only hold out for 5, okay? Now the second case is that x3 is 4, okay? Then x4 is either 5 or 6, but we, 5 or 6, like if it's 5, then we have a difference of 4, and if it's 6, then we have another difference of 4. So if this is 4, then we can only hold out for 4. So in both cases, in all cases, for k equal to 4, we can only hold out for 5 terms, okay? And that would look like something like 1, 2, 3, 4, 5, or 6, or 7, or 8. So k equal to 4 must happen in 5. And I think that's enough to kind of convince ourselves of this pattern. So let's go ahead and try to prove it. So what we want to do is prove that within the first k plus 1 terms, there must be two terms which have difference k. One equals x1 Cool. So these numbers, x1 to xk plus 1, they could be anything from 1 to 2k. And they're distinct, right? Because this is a strictly increasing sequence. So we have 2 to the k numbers that we can work with, right? From 1 to 2k. That we can, 2 to the k candidates, right? That we could possibly pull from. And we want to show that no two of them. So we want to be able to pick k plus 1 numbers from 1 to 2k, 1 to 2k, such that no two of them have difference k. And what we can do is apply the same idea as in problem 33, that whole pairing idea, right? If we pair these numbers up, 1k plus 1, 2k plus 2, up to k comma 2k, right? Here we have k pairs of numbers. So if we pick k plus 1 numbers total, we must pick 2 numbers from the same pair. And let's say those 2 numbers are these 2. And then boom, we found two values which have difference k. All right. And that is the solution. So it uses a similar kind of pairing idea to the one we used in the subset sum. This is I would say this is like more of like a medium like level problem. It's definitely you know, not super easy, but I think the solution doesn't come as much out of left field as some of the other ones. Now, I'm going to talk about my mistake on this problem. Okay, I made a big mistake. I actually didn't solve this problem. Okay, and the reason was because I jumped way too quickly to trying to prove the statement without considering small cases first. So, at least personally for me, like oftentimes I have a temptation to just want to dive into a problem, to dive into like the general kind of idea of a problem. But like it's important that you're patient with yourself and that you kind of admit to yourself, like, I don't really know what's going on. I should test small cases here to get a better feel for this, right? And once you test small cases, the idea of looking from 1 to k plus 1 is like, comes kind of naturally, right? So that has to do with like, I would suppose a bigger idea is like, that has to do with don't jump to conclusions, okay? Specifically the conclusion. Now, usually when I say don't jump to conclusions, that means don't jump to a conjecture that you haven't really fully, don't like 100% believe a conjecture you've made until you've actually proven it, right? You always have to have a degree of skepticism. That's what I mean by don't jump to conclusions usually. But in this case, don't jump to conclusions applies to your method, like the way in which you solve a problem. You don't want to jump to the conclusion that you actually know what you're doing, right? Like too quickly, okay? Or jump to the conclusion that, oh, I don't need to test small cases. Like I'm above that, right? Like, and for some problems, you know, for some problems, you don't need to test small cases to prove that something is true. Like, you know, certainly, you know, if the problem is kind of below your like ability level. But, you know, for this problem, I kind of, I didn't, you know, it's not like I explicitly assumed that I was like too good for this problem, but by not testing small cases and not being patient with trying to understand what's going on, I kind of implicitly made that assumption, right? And it cost me a lot, right? It cost me a lot of time and a lot of headache because I wasn't able to solve it, and even more headache once I realized the relative simplicity of the solution compared to what I was trying to do. All right, one more problem. Thank you to the one person who has stuck with me. One more problem. And oh yeah, so I'm going to skip problem 36 because admittedly I haven't reviewed it enough and I don't really want to kind of go over it live if I haven't reviewed it a lot myself. I did solve it kind of, but not explicitly, and I don't want to be troubleshooting live, although I know I do that sometimes. Okay, the last one we're gonna look at is problem 38. Now, personally, I love the statement of this problem. I think it's really good problem statement, okay? The reason is it's so simple and straightforward compared to the other problems. Like, all these other problems are like, oh, like, you have this set of 1985 integers, and it's like, they have primes less than 26. You gotta show that some subset of 4 has fourth power. It seems so like kind of contrived. But this problem statement, all it's saying is, here's a Fibonacci sequence, something that we've seen, okay, very common. Show that some number is divisible by 1,000, right? I mean, you can explain it just so, just like that. That's not to say, of course, that it's an easy problem, okay? It still requires a good amount of thinking. So we want to show that there's some positive term of the Fibonacci sequence that's divisible by 1,000. Now, what we're going to do is we're going to track the Fibonacci sequence mod 1,000. Okay. Now, like, if we try to, well, how do I explain? So instead of like looking for whether a number is divisible by 1,000, what we'll just do is we'll write we can imagine sort of each number we take mod 1,000, and we repeat the Fibonacci process, and we want to show that some number eventually is 0 mod 1,000. Okay. This also, like, I've used this before. Like, if you track the Fibonacci sequence mod some number, it still like behaves exactly like the Fibonacci sequence in terms of like the rule still kind of applies. Okay. All right. Also, a quick note: 1,000 is almost definitely arbitrary. Okay. Now, I know you think 1,000 is just such a nice number, right? But this is largely a result of the decimal system that we work in. Okay. And not really anything deep mathematically. All right. This is a whole nother discussion, but like the number 10, we like to think, oh, 10 is such a nice number because when you multiply by 10, you add a 0, right? But really, 10 is not that nice objectively of a number. It just has to do with the fact that we work in the decimal system. If we worked in base 7, you would think 7 is like the best number in the world. Okay. Really, in my opinion, what defines like the niceness of a number is how many factors it has, right? Exactly how many, like 360. 360 is like, in my opinion, objectively a nice number just because it has a lot of factors and such. But anyway, I digress. Okay. All right, well, not quite. Let me not digress quite. This is important though, because it kind of tells us like the way we want to tackle this problem is not by like analyzing the properties of the number 1,000 to try to see what's special about 1,000 that, shows that some number is divisible by it. It's probably arbitrary. Okay. The only thing that I can think of about 1,000 that would be useful is that it's a perfect cube. But that I will just save you time that doesn't come up. Now I digress. Okay. So first thing we'll look at is Fibonacci sequence mod 3, mod 4, mod 5, mod 6, and we'll try to get a feel for kind of how that evolves. Now I'm not going to actually write all of that out, but what you eventually reach is that. Oh, let me try to find. Oh yeah, okay, here. So what you eventually realize is that so like mod 3, I'll just write mod 3 real quick. So we always start with 0, 1, then we get 1, 2, then 1 plus 2 would be 0, mod 3, okay? Then 2, 2, 1, 0, 1, and boom, we have 0, 1 appear. 0, 1 appears again, right? At the very end here. And that means it's going to cycle. Right? It's going to cycle in the exact same way. So our cycle here, this is our cycle, and it's of length 8, and that's going to repeat. Okay. Then, if you do mod 4, you get a similar situation where you get this cycle that cycles every 6. So that'd be 0, 1, 1, 2, 3, 1, 0, 1. cycles of length 6, and mod 5, you get a cycle of length 20, and mod 6, you get a cycle of length 24. Now, that isn't super important. That isn't important for the solution. The fact that, now I was kind of looking at this, I was trying to see maybe if there's some kind of pattern in the cycles, 8, 6, 20, 24. I couldn't really think of a pattern. Maybe there probably is some kind of pattern to these numbers, but I kind of realized it wasn't super relevant to the problem. But there are a couple important things that you noticed from that, or at least I noticed from doing this, right? Just looking, these lower mods. The first is that, well, a cycle always happens, right? There's always a cycle. And we can think about why that has to be the case. Let's think about why it might not be the case. You might have a situation where you look at mod 1000, you have all these different mod values, right? And it just doesn't repeat, right? That, like, those mod values, they just don't repeat, right? And I mean, if you haven't seen this before, you could kind of convince yourself that might be the case, right? But in fact, it must repeat, and no matter what the mod value is. The reason is that so the Fibonacci sequence, at least the future of the Fibonacci sequence, is always determined by the two current terms. Those two current terms completely determine the future. So the possible pairs of current terms, there's a finite number of those given a certain mod. So mod 3, there's only going to be 3 squared, which are 9 pairs of terms that you could have, right? Mod 1000, you could only have 1000 for the first and 1000 for the second. What that means is, like, it's an infinitely long sequence. So there must be two points in the sequence where you have some pair of mod values, let's say 567 and 789, and then another occurrence of that pair, 567, 789, because there's only a finite number of these pairs, and there's an infinite number. It's an infinitely long sequence, so some pair must occur twice. So that tells you that a cycle has to happen, because if you think about, you have that pair, and then you have the second occurrence of that pair. Everything in between is gonna, be the same. Everything, you're gonna have like something happen in between, and then once you get to that next pair, that is going to completely determine the future of the sequence, and you're going to have the exact same thing happen, the exact same cycle. Then you're going to hit the exact same occurrence, the same distance away, and these mod values will cycle. Okay, that's important observation number 1. A cycle will always happen, and the reason has to do with the finite number of pairs that you could have mod a given number. And again, this is true in general, right? Kind of confirming our initial observation that 1000 is probably arbitrary, right? The second thing, which now I sort of noticed that fairly quickly just from experience, but the second thing that I really had difficulty understanding exactly why was that these cycles will always cycle 0, 1 will always be the beginning of these cycles, okay? So you could imagine a situation where you have a lot of numbers, right? And then at the 20th value in the sequence, then a cycle of length 7 starts, right? So you could have like a bunch of numbers at the beginning, and then a cycle starts, and that cycle continues. This happens in infinite, in decimal representations of fractions. So like 1/6. 1/6 is 0.166666666. So you have like 0.1. 1 is like not part of the repeating term not part of the repeating at all, right? It's just kind of a term that's there. And then the repeating part starts later and it continues. I believe like 1/13 or something has a similar situation, although a lot of numbers will repeat. Like 1/7 is 0.142857, and then it'll be 142857. It'll always repeat like the beginning block, okay? So anyway, that whole what I'm trying to say is I couldn't really justify to myself why it always repeats the beginning block, because like I said, there's a lot of examples of repeating things that don't repeat right away. But it turns out that this is super crucial, right? So now the way that, And also, okay, second thing is, if you do have a cycle, right, of these mod values, how do you know that you always get there's always a 0 in that cycle, right? How do you know that there's always a number divisible by 1,000 in that cycle? Because if there's not, then you would have no number divisible by 1,000, because that cycle extends off to infinity. Now the key idea is this. Well, actually, it's not like this. It's kind of a bit of a long explanation, but let's say your cycling mod value is mod 10, okay? And let's say 5, 4 is the beginning part of the cycle. That's the first pair that repeats, is 5, 4, okay? And so somewhere later down the line, 5, 4 repeats. So the key idea is that you can, if you think about, okay, what is the previous term here, right? How can we backtrack? Well, if this is 5 and this is 4, then this must be 9, okay, if we're looking mod 10, right? And in general, with the Fibonacci sequence, if you're given any two terms, you should always be able to backtrack as well, right? And so then we could backtrack again. So we could say this is 9, this is 5, so this must be 6, right? And the idea is, if you have two pairs, right, which are the same, my hand's kind of gross because of the marker, but you have two pairs which are the same, then you know that, like, if you go backwards one, those two pairs must be the same. And then you go backwards one again, those two pairs must be the same. And you can backtrack all the way to that beginning 0, 1, right? So somewhere in here, that beginning 0, 1 has to pop up, right? And what that means is, well, if the beginning 0, 1 pops up, then that's the pair that is the first that repeats, right? And that's why the block will always repeat from the very beginning, right? And that also tells you that later down the line, you must have a 0, 1, which comes up again, and so you must have a number divisible by 1,000. And again, well, in this case, 10. But like I said, this works in general, and it again confirms my conjecture that 1,000 was completely arbitrary. You could say, prove that some number in the Fibonacci sequence is divisible by 7,952, and there you would be able to find one. And that's actually, that's actually a pretty interesting thing about the Fibonacci numbers, that, like, you can, no matter what number you give me, I can always find an infinite number of numbers which are divisible by that one, right? Okay. Now, if you were to prove this, like if you wanted to prove this mathematically, you would use like a sort of backwards induction, okay? So I guess this is actually kind of an induction problem a little bit. So what you would say is something like, suppose that, so use a pigeonhole principle argument to show that there must be some two pairs which are the same. And then you say, let's say that those occur, or let's say f sub a plus 1 equals f sub b plus 1, right? And you say, this is the first pair of Fibonacci terms that repeat. This is the first pair of Fibonacci terms that repeat, okay? Or, yeah. So then, f sub a minus 1 f of a equals f sub b minus 1 f of b, right? You can show that using the recursive formula. So, but this is supposed to be the first one, right? So if this is the first one and it occurs later down the line, we just found one that happens earlier. So it can't be the first one, unless this is the actual first term and we can't go backwards, right? So like you can use like a sort of, this is like this isn't called infinite descent, okay? It's kind of like, I don't know if you would call it finite descent. It's an argument. It's a form of proof by contradiction that allows you to basically show that, like, in this case, show that, you assume that like something happens like later, and then you say, oh, but then if it happens later, then it must happen earlier. So then it must happen at the very beginning, something like that. That's kind of the general idea. So the only way that this can be the first repeating block is if these are the literal first terms, and you can't do this backwards thing. And so that tells you that 0, 1 is the first pair that repeats, and then you found your number. That's a little y,000 later down the line. Okay, so all right. So thank you for joining me. The one person who joined me, you're a real trooper. So thank you for that. Like I said, I encourage you to do the problems right beforehand. But obviously, I mean, it's the summer. Like, I understand if you're just trying to chill out a little bit. But I would say at least before these streams, take a look at the problems and make sure that you understand the premises of the problem, because otherwise you may have a difficult time understanding the solution. And as always, smash like and subscribe. And I hope that you're having a good summer, or if you just started summer, I hope that it's good. Hags.